This is not an m=3 pattern. There must have been a bifurcation leading to that because it's not even. So what is the bifurcation? We saw it. m=3 looks like this, right? That's the m=3 one. And how do we get to Mercedes? Well, it's a complicated route. Here we do this, and you remember I said that trigonometric, they can evolve like this, and it eventually makes something that we called Marigold. Oh, okay. We got all these different patterns, of course, and we wanted to give them names, Mercedes and Mitsubishi, right? This is what the Mitsubishi looks like. So naturally, I looked for names, car names for the other ones, but I looked on the web, I looked at all the different car logos, and none of them look like this, and none of them look like this. So I had to go and give them flower names. I just don't want any more car names. This Toyota looks a little bit like that, but it doesn't have the basic property. That is to say, Toyota, its symbol is like this, and this is not threefold symmetric, right? So I couldn't call, I mean, that's very important to the study. I would have liked to have called that, that branch Toyota, but I couldn't because it really doesn't have the right symmetry. Okay, so anyway, we have this marigold thing, and so what kind of bifurcation is this here? What kind of bifurcation is this? Circle pitchfork, please. Who didn't say circle pitchfork? I'm going to be really mad. I mean, this is a circle pitchfork, right? Yeah? Right? Any phase? Okay. Now, as we said, this has extra symmetry. It doesn't just have the symmetry that of the reflection and the 2π/3 rotation. It also has the symmetry that purple and yellow are the same. There's another symmetry that's broken over here. And now you see yellow and purple are different. You have three yellow guys here and purple on the edge. This is different. And there's another one that exists another branch that would be the opposite. And these we called Mitsubishi. As I said, I happen to have or had a Mitsubishi until it broke down. Then there's a saddle node bifurcation, and this ends up looking like we gave this a name cloverleaf. And then there's another bifurcation. Finally, for the very first time here at 5503, this branch here, finally this is stable. So you imagine you have this very, very tortuous route, and without steady state sound, without Newton's method, you would never know any of this. The only thing you would know is this thick line. You would know these pictures, yes, but none of these other pictures could you get because they are unstable. You would just have these pictures, and they would end here. Why? I don't know. But here now you know everything from a bifurcation theoretic point of view. You might say, and what's the point of knowing all that? And that I have no answer to. But this is, if you like this kind of thing, this is how you must learn it. Okay. So I have lots of pictures of, this is another view of it. Then I have calculations done in spheres. Again, the thick lines are the steady states. The thin ones are, excuse me, all of them are steady states. So the thick ones are stable. The thin ones are unstable. This is with rotation, so this symmetry is not O2 but SO2, and hence you get this rotation in the same direction or the opposite direction, but usually the same rotation as the rotation of the sphere. Here we have something called snaking, which has lots and lots and lots of branches, each adding one roll at a time. This one is one of those branches. This is another one, and another one, another one. They each add a roll, and these are all unstable states. But eventually, well, there's no but a new physical phenomenon discovered in the early 2000s. More things. Let's see. Let me ask, okay, I'm going to talk about methods for calculating eigenvalues. So let me ask if there are other questions concerning Newton's method for steady states.
In the Newton's method, you can have something which gets into a loop, right? Like a period 2 cycle.
Newton's method is only finding steady states. If you wish to find a 2 cycle, there are methods for doing that as well. One of them could be that you look for the map applied twice.
I mean, like one of the limitations of these methods, like you can have like, if you start with some initial guess, it can get into a cycle and not find the solution.
I see. Sometimes I would say, okay, the theorem about Newton's method that works in my experience, it will find a state if you are close enough. It will not find a state from who knows where, but if you're close enough, it will find a state. Hence, it is used It is a good thing to use it in combination with time-dependent solution because you go somewhere and you get to something and then the state disappears, and so you have some good guess here to continue it, something like that. As for when it fails, yes, it does fail. And so I would say that the cases in which it fails are pretty much summarized by you weren't close enough. Are you thinking of this Julia set thing where you're looking for the roots of ZQ, the Mandelbrot set?
No,
ZQ?
like in general, I was just thinking like if it could potentially get into a cycle
Yeah.
if your guess is like bad enough or something.
I think if your guess is bad enough, you could just go to infinity.
Yeah.
Very easy for Newton's method to diverge.
Mhm.
I can say one more thing then about stasis. Okay, supposing you were, how could you do this? I said that you could go around, you could find, your branch would disappear by saddle node bifurcation. But supposing you're increasing the Rayleigh number, how are you going to really find that out? You get here and you find, oh, there's no solution. So Newton's method fails, just as you say, there is no solution. So what can you do about this? If you suspect you are near a saddle node bifurcation, then what you can do is use what was the control parameter, what you were controlling, the Rayleigh number or the Reynolds number, as an unknown, and fix instead one of what was previously the known ones. You can fix a value of the solution and find the Reynolds number. And how do you do that? Okay, let's write out equation. Here I put the Reynolds number explicitly in front of the nonlinear term. We're going to have an extra unknown, which is the Reynolds number, and so we need an extra equation. So here I've said some projection of U and R onto some value. So some easy possibilities. Let us set the Reynolds number. That's what we're usually doing. But we could also set that some component of the solution has some value. What does our Newton step become? Well, let us expand our function about capital U and capital R with a little decrement, little u, little r. We're going to expand this as we usually do. So we have capital R minus little r times n of big U minus little u plus L big U minus little u. Let's do a Taylor series as usual. We have R times n of u, yes. We have L capital U, those are all 0th order terms. Then we have capital R times the linearization of n about u on little u. Then we have little r times n of big U. These are linear terms because they involve one power of the little guys. This involves one little u and one little r. And then we have minus LU, that all of these are linear terms. Then we would have other terms that involve little r and little u. Or since this is nonlinear, we would have also one that involves n of, we have little u twice, big R, and little u dot grad little u. But all those are higher order terms. We forget them for our linearization, just as we do for linear stability analysis. And so our Newton's equation to be solved, we're supposed to find the little u and the little r, which satisfy this equation, as well as the linearization of this equation. So we set up, whereas before we were merely having matrix times little u equals right-hand side, now we have matrix times little u plus the unknown little r. The little r multiplies big N of u. Okay. This is the matrix statement of this equation here, where little u and little r has been added to little u at the bottom of the vector. So our vector is now no longer of length 1 million, but 1,000,001. And we have here this is a million equation, and this is one more equation. So this is of length 1 million, and this is 1. And this is a block that's 1 million by 1 million, and this is a block that's 1 million by 1, and this is a block that's 1 by 1 million, and this is a block that's 1 by 1. And this equation, this is the matrix way of stating the linearization of the goal. So again, we solve this iteratively. We multiply by this equation by L inverse. And by solving with, by finding a new little r, we adjust the Reynolds number, and we end up being able to to go around the saddle node. We can also do this for traveling waves. I said I misunderstood your question, and I thought you were talking about using Newton's method to find cycles, but you weren't. You were talking about how Newton's method not working. But you can use Newton's method to find traveling waves, because traveling waves, we discussed this in our spatial analysis chapter, which we just finished this morning. Traveling waves are steady states in a moving frame. If you find the right speed, you can use the speed as an unknown. So this is the same transformation that we used before to zeta. So we end up with, this is the equation satisfied by traveling waves, where d by dt has become c dxu, or rather minus c dxu, but then we brought it over from the other side. You will remember this is the same equation that we looked at before. This was c times the velocity, what we did in the very first part of the class this morning when we were finishing reaction diffusion. We had c times the velocity. I said that was a friction term, right? And now we have it here in this numerical context. So again, we can expand. We say our big C, our big U does not satisfy this equation, but let me try big U minus little u, big C minus little c. Let me eliminate the quadratic terms and the zeroth order terms, and this is the equation that I get that little u and little c must satisfy. And I can solve that and get traveling waves. Okay, so 15 more minutes for eigenvalues. It's not, I mean, it's been a long time, I know, but on the other, we did start 15 minutes late, so it hasn't been quite as long as it seems. And we did take about 10 minutes. I mean, it's been long, yes, I agree, but okay, so eigenvalues. As I've said any number of times, it's much more tiring to listen than to speak. I'm very well aware of that. The speaker is all, I understand people feeling this word in French, abattu, all the words have fallen on you. So I understand that it's hard for you to listen, harder for you to listen than for me to speak. Okay, so linear stability analysis. We want to find the eigenvalues of this. Just as with, okay, I said that Newton's method doesn't always work. However, if you're close enough, Newton's method does always work. And then all you have to do is solve a linear system. And you can always solve a linear system. It just might be costly. It might take a time n cubed. You might be waiting for the next decade to get the solution. Same thing with linear stability analysis. This is a linear problem here. You are trying to find the eigenvalues of this Jacobian, L plus n sub u. I think you all know by now what kind of operator this is. This is the Navier-Stokes operator, where you've replaced big U by big U dot grad, big U by big U dot grad little u plus little u dot grad big U. Yes, everybody knows what this is. You're trying to find its eigenvalues. You can construct the matrix. The QR algorithm is guaranteed to find the eigenvalues of a matrix. You can send it off to QR. But if you are talking about a million by million matrix, you will be waiting a very long time, and it's probable that the computer will even have been replaced by another computer by the time your calculation will be done. So you can't do that. QR deconstruction, this is the way to find all the eigenvalues. It takes a time n cubed. So this is the problem in CFD. This is the problem in numerical analysis. This I don't think will be solved. So I don't think will be reduced. I think this is just how it is. The linear one, the linear iterative method will be, I think, solved sometime. That there will be a good iterative method that will find solutions to AX equals B in less than the current time. Just as with linear solution, there's QR, which will always work and which will take a whole long time and a whole lot of storage. There's an iterative method, and again, iterative method that requires only that you know how to act with the matrix. Matrix action is much more manageable than doing anything else. You don't have to create the matrix. It's basically something like taking a time step, like taking a Laplacian, like doing u dot grad little u. You use all the machinery you already have. That's our goal, is that we only have to take actions. Okay. And there's the same considerations as before. There exist iterative methods that find eigenvalues, but first of all, to make all the eigenvectors, You would need m independent directions. You have to create m vectors. And creating each vector requires a matrix vector multiplication, which takes the time m squared, and hence it takes the time m cubed, like QR decomposition. There's no miracle. In the worst case, both take the time m cubed. As before, you can win by iterative methods in the following way. One of them is that your matrix product need not really take a time m squared. It probably takes a time more like m if your matrix comes from some continuum mechanics problem. You have your x and y and z directions which are decoupled, and or you're like a Fourier transform which may be full, but in fact, all those things make your actions much more like linear in the number of operations rather than quadratic. That's the first thing, and that we talked about. I'm not going to talk about it anymore. The second thing is we're not looking for all the eigenvalues, or maybe we are, but too bad, you can't do that. We're only looking for some. We're looking for the ones that bifurcate. We've talked about that any number of times. We have our eigenvalues. We have a spectrum. It looks, here's our complex plane. Here are our eigenvalues. And we're looking for when they cross 0 so as to have a bifurcation. Okay? So we only want a few. And so we don't have to create m independent directions. But let's see how we can aim it at the eigenvalue, at the desired eigenvalues. We talked about acting with a matrix. If we act with a matrix, well, here we are. We're making AU, A squared. Okay. How many of you have heard of the power method for finding dominant eigenvalues? How many of you have heard of the power method? If you act over and over with a matrix, write an initial vector as a sum . We have U equals a sum of, these are the components in the different eigendirections, right? You can't do it. If you could do it, you would know all the eigenvectors and you wouldn't need to do anything more. But just theoretically, we can write it this way. If we act with A, then that is like multiplying. Each eigenvector gets multiplied by its eigenvalue. And if we do this over and over again, you're multiplying by the power of that eigenvalue, and hence you're going to go to one eigenvector, the one such that lambda 1 is bigger than the other ones in absolute value. Right? So that is the way to find the largest eigenvalue. And that's what's written in this top line. There's a generalization, supposing you don't just want the top one, you want a couple of them. Then you take a bunch of the powers here, you arrange them, you orthonormalize them, and you arrange them in a matrix. It's called V here. And you approximate your method by the inner product of the matrix acting on a vector with the vector. Those of you who have done quantum mechanics or something, and some of you are here physicists, this is something like, there's some name for this. This is like the representation of A on a small basis, I think. Or anyway, you don't have to be a physicist to know that name. This is a representation of A on this small basis. Yes?
So you know how you said you can find the eigenvalue with the largest magnitude using that? But when you look at bifurcations, don't you want the ones with the smallest?
Oh, I was getting to that. I was getting that. Thank goodness somebody said that. Precisely. Absolutely. Next page. Here I was just saying, if you want to find a few of them, there's a generalization of the power method which gives you a few of them. Okay. Now, as you say, that's exactly the wrong ones. As we discussed many, many times today, we have eigenvalues that are over at the next building, right? The eigenvalues are Laplacian, all those minus k squared. I talked about minus 30,000, minus 100 million, and they're all the way over there. And what eigenvalues are those? They're the eigenvalues that correspond to the smallest resolution you have in your problem. They're exactly the ones that you're counting on for detail, but you're really not interested in them at all, especially given that if you increase the resolution, they're going to change. Anyway, they're not the ones you want. The ones you want are close to 0, as you say. They are the smallest in magnitude. Not quite, because a Hopf bifurcation might have a big imaginary part, but that I don't really know what to do about. Some people have thought about it, but I have not studied this yet. Still, let's say that on the whole what you want is the eigenvalues closest to 0. So here's the picture. These are the ones you don't want. They're the largest ones. You do not want to act with A over and over, which is just as well because you don't have A. Fortunately, it turns out that if U and lambda are the eigenvectors and eigenvalues of a matrix A, then for any analytic function f, the eigenvalues of f of A are that function on lambda. And that seems like a mysterious and valuable and unlikely property, except we showed it in the very first class. How did we show that? When we were showing the exponentials. We showed it, basically it arises from the fact that we can write f of A as, my favorite tool, Taylor series. Right? So we write, we have A equals E lambda E inverse, where these are the eigenvectors. So we write f of A equals f naught plus f1 E lambda. Right, we did this for the exponential, so you saw it already, plus f2 E lambda E minus 1 times E lambda E minus 1, right? So these cancel. This becomes a lambda squared. It's easy to take diagonal, and we end up writing this as E times f naught I plus f1 lambda plus f2 lambda squared, etc., with an E at the end. And this is just f on the, this is just f on lambda. And we know that we can carry out functions on a diagonal matrix by just taking the function on the elements, right? So you see that? You just have the same eigenvectors, and you have just a function there. So we can use any function we want. A very good one, that gives you the right answer, is the exponential. And that's not by chance. I've said this to some great numerical students. Oh, how clever to think of that. No. It's not, because the whole reason you're interested in these eigenvalues to begin with is because you have an equation, du dt equals au, and you know that u of t is equal to e to the at u of 0. And hence, really, what you're interested in is basically the eigenvalues of the exponential. That's the ones you're interested in. You're interested in the eigenvalues of the exponential that are largest. And so, indeed, all of these with their minus values, they were very big. But you take e to the minus something, and you get 0. And you take e to anything on the imaginary axis, even with big imaginary part, and you get something that's on the unit circle. And so those are really the ones you want. What you want is the ones closest to the unit circle. So that would be great, except that, in general, we don't have the exponential. You recall, again, we've shown this many times during this, what we have is a numerical method that, say, backward Euler, forward Euler, or something like that, right? I plus delta Tn mixed method that we were talking about. And what is this? This is an approximation to the exponential that works for small delta t. For small delta t, this is like the identity, and hence each time you're acting with almost the identity, so you can see you're not going very far. What you'd like to do is take a big exponential and just do it, but you can't. So what I'm recommending instead is taking the inverse. And the inverse is turning, again, these are the eigenvalues you want. And the big ones here, big negative ones, have been turned into small negative ones. And these that you want have been turned into this. Some of you have heard of RPAC, right? Well, many people have heard of RPAC, or no? What RPAC does is effectively, it takes a function which is a polynomial of the matrix. Okay, and you might say, how does it know what to do? Well, it does it dynamically. It chooses the polynomial based on what it learns about the matrix as it goes along. It chooses the coefficients in some clever way to aim the spectrum the right way. Anyway, so this is what I was saying before. Exponential would be fine, except that we don't have the exponential. We have something that's very close to the identity. And each action of this operator, okay, what you're looking for is, okay, you saw this calculation, oh, it went away already, the one where I said that A on U was UK lambda k psi k, right? So let's take that to be the first two, A1 lambda 1 psi 1 plus U2 lambda 2 psi 2. You can see that what you're trying to get it to be psi 1. So this is lambda 1 plus U2 lambda 2 over lambda 1 psi 2. Do I have this right? Did I do that right? Anyway, yeah, I did this. No, excuse me. Like this. Yeah, you'd like to get this term. You'd like this term to go away, right? So what you want is for this thing to be really small. Or what I wrote was the opposite. What you want is it to be okay. What is it I'm trying to say? And if what you're talking about is not acting with A but acting with the exponential, what you'd like is for this thing to be really small. But it's not going to be. If this is like the identity, if this is close to 0, what you're going to find is that this thing is very close to 1. I wrote the opposite here. I wrote the inverse of it. What you'd like is for this to be really, really small so that you're really getting rid of this. But you're hardly getting rid of it at all. Okay. So it's slow. It's effective, but it's slow. It's going to take you 10,000 steps, 30,000 steps, lifetime stepping. Finding the inverse, acting with the inverse. How can you act with the inverse? Well, it's the same thing as what we talked about for the steady state solving. That is, what you want to do is, well, act with the inverse. So let's write that as a matrix equation.